For quite a while, people have envisioned what life might resemble in different universes. On account of the James Webb Space Telescope, the most remarkable telescope in existence, that question can at last be answered. While observing the nearest star system to us, Proxima Centauri, which is just 4 light-years away, researchers have seen several curious irregularities from one of the planets in the system, Proxima B. These peculiarities, called fake lights, have confused the best personalities in mainstream researchers. But what are they? Do these lights suggest the presence of wise life on the world? Join us as we explore James Webb's unnerving discovery of city lights that change everything. The main life that we are currently aware of is on Earth. Beginning from the start of evolution, people have questioned whether there is life elsewhere in the universe. To do such an interstellar pursuit, American cosmologists Jill Tarter and Thomas Pearson set off the search for extraterrestrial intelligence, SETI, project in 1984. The charity's mission is to gather spaceborne radio transmissions. Radio waves can travel farther and are thusly bound to be detected by the 42 radio telescopes that make up the exceptional Allen Telescope Array in the Californian Fountain Mountains, since they are less scattered or absorbed than other types of radiation. Yet, in the beyond 30 years, no unquestionable alien transmission has been found. After that, the James Webb Space Telescope's successful launch boosted the quest to examine a range of distances and unseen planets orbiting faraway stars. The largest telescope on the planet, which is floating about 1 million miles from Earth and equipped with incredibly sensitive detectors, will be used. Quite a long time ago, there were no known planets outside those in our local planet group. Yet since then, more than 4,000 planets, also referred to as exoplanets, have been discovered orbiting other stars. According to NASA, the universe might contain trillions of exoplanets. The earliest signs of something going on under the surface beyond our local planet group might be found in extraterrestrial vegetation. The GY shuttle turned its equipment back toward Earth when it was on its way to Jupiter and found an unequivocal sign of the presence of plants. The instrument detected the vegetation red edge, a blend of red and infrared lights reflected by plants. For example, a planet like Earth that is covered in a jungle should have areas of dominance for an easy-to-detect red edge. The JWST will measure the red edge of faraway, Earth-like planets in the habitable zone around stars. They could be significant indications of something going on under the surface in the exoplanet atmosphere. When sunlight crosses a planet's star, the JWST might be able to detect it as it enters its atmosphere. The light's missing frequencies would then be found through spectroscopy. Ions and molecules in the atmosphere absorb specific frequencies, creating a characteristic fingerprint that the JWST can recognize. This method might be used to determine the composition of the atmosphere and whether life is possible. Most likely, life could exist on Earth-sized planets with atmospheres like our own, with the prevalence of oxygen, nitrogen, and carbon dioxide. By searching for elements that aren't generally present, one might be able to identify technological life. Chlorofluorocarbon, CFCs, produced for use in refrigeration and cleaning products, would likely be observable to millions checking Earth's atmosphere from a distance. If the JWST found CFCs in planetary atmospheres, that would be a clear sign of advanced life. Actually, life on exoplanets might not at all look like life on Earth. Sometimes, even natural life like extremophile species can seem alien. This is a group of organisms, primarily bacteria, that can thrive in conditions where other living things would perish. Some can survive temperatures up to 250 degrees Fahrenheit, some can survive colds as low as 4 degrees Fahrenheit, and some can survive regions of dominance with pH levels under 3. Others can be found on Earth where we wouldn't expect to find any life at all. But since planets like Earth are more likely to support life than planets with extreme temperatures or acidic environments, it might be wise to start with those first. Prime candidates could have temperatures that allow liquid water to exist on their surfaces and orbit a stable star. The classification for our Sun is a yellow G-type star. These stars are rarer and typically have shorter lifespans. In our universe, the likelihood of focusing on planets orbiting around red dwarf stars, which are more frequent and have lower luminosities and temperatures than the Sun, is higher. There is additional opportunity for the evolution of life and development to produce complex life forms because these stars have longer lifespans. Primarily around 40 light-years from Earth, the TRAPPIST, one planetary system will be the subject of JWST's first mission. It orbits around a quiet red dwarf star with 7 Earth-sized rocky planets. 3 of the rocky planets in the so-called habitable zone could have liquid water on their surfaces. The TRAPPIST-1 star, despite having a much smaller and colder mass than our Sun, emits light that is similar to that of Earth due to the close orbit of its planets. The most visible chance so that people might see city lights outside the planetary group is Proxima Centauri, a red dwarf star that is 4.25 light-years from the Sun and our closest star. Proxima is times fainter than the Sun, so a planet should be times closer to it than Earth is to the Sun for it to support life because of liquid water. In August 2016, astronomers found a planet with 1/3 the mass in this habitable region in a Goldilocks-like habitable zone where the light intensity is perfect to melt water. Proxima B circles Proxima Centauri. It's possible that Proxima B is an airless dead planet, given that it orbits its red dwarf star, Proxima Centauri, at a distance of just 46 million miles. The planet Proxima B is in a close orbit that exposes it to strong solar winds that can completely destroy its atmosphere. It also provides ample sunlight for temperatures and liquid water that are similar to those on Earth. Due to its proximity to the star, Proxima B is believed to be tidally locked, continuously showing the same side to the star as the Moon does to Earth. Proxima Centauri is around 1/8 the mass of the Sun and emits significantly less brightly than one would expect for a planet so close to its star, only 5% of the Earth's Sun distance, which might be expected to be a scorching ash. Fluid water could easily exist on Proxima B as long as the planet has an atmosphere to hold heat, since the total energy reaching it from the Sun is only 65% of what Earth receives. However, the planet is not friendly to life. It is indeed tidally locked, which means that it always faces the same direction toward the star and undergoes extreme temperature changes. The planet also receives 100 times the amount of high-energy radiation as Earth does because of its proximity to Proxima Centauri, including X-rays and ultraviolet light. Proxima B is also bombarded with high-energy particles during star eruptions. Unless it has a protective magnetic field like Earth, however, there are certain plausible circumstances that could make it a pleasant world. Unfortunately, models suggest that the atmospheres of tidally locked planets may be prone to rapid breakdown due to the freezing out of volatile gases on the night side. A planet's atmosphere can be replenished by volcanic activity, and for planets with strong magnetic fields, this atmosphere is less likely to escape. Since we know nothing about Proxima B's volcanic activity or magnetic field strength, we couldn't technically predict whether the planet has an atmosphere. Yet, since an atmosphere implies the presence of oceans, and the two taken together suggest the existence of life, we are eager to find out. Assuming that Proxima B has a developed civilization, it could have solar panels covering the day side to generate power to light and warm the night side, which would otherwise be too cold and dark for comfortable habitation. The discovery of Proxima B has triggered a race to determine if it transits its star's face as seen from Earth. These transits would allow scientists to determine the planet's size and mass, which would then enable them to determine its density, knowing that would validate the planet's rocky composition and provide information on the materials used to form those rocks. During a transit, starlight could reveal the nature of the planet by passing through its atmosphere. However, the likelihood that the orbit will be in the correct alignment so that scientists could observe a transit is only 15%. The star's propensity to erupt also complicates matters. Cosmologist David Kipping of Columbia University says the star is unstable, as the star's heat makes a rocky planet absorb sunlight and re-emit it as infrared light. However, rocky planets emit a distinct type of infrared radiation from stars like Proxima Centauri. Furthermore, the James Webb Space Telescope was made specifically to focus on infrared light. Proxima B's infrared intensity signature is the key to identifying the planet's atmosphere. Moreover, the infrared portion of the spectrum has signatures for water. The JWST will be able to detect city lights on Proxima B's night side, even if they were as faint as what our civilization currently uses on the night side of Earth. Webb could detect artificial illumination for as long as it was restricted to a frequency band that is 10 times narrower than that of Proxima Centauri. Proxima B's day side is heavily covered with solar panels, owing to its unique spectral edge's ability to reflect starlight. As Proxima B rotates around its star, day and night cycles are indistinguishable. Cool night lows follow daytime highs, The difference in temperature between day and night, however, depends on whether the planet is entirely made up of bare rock, as both an atmosphere and ocean moderate intensity. If there isn't an atmosphere, Proxima B's day-side and night-side temperatures will vary more. In fact, since the day-side will re-emit all of the energy it receives from Proxima Centauri as a black body, we can calculate the exact amount of black body radiation that should be present. The night side, on the other hand, will appear to be a frozen wasteland. If the temperature difference between day and night is less pronounced, we can infer the presence of an atmosphere. Fortunately, it will only take the JWST 112 Earth days to measure the radiation from Proxima B's two faces after it has successfully completed its orbit around the star. If Proxima B has an atmosphere, the next step will be to analyze its composition. The presence of gases like oxygen, water vapor, and methane, in particular, could indicate the presence of habitable conditions if not actual living things. To achieve this, however, we must effectively capture starlight as it bounces off or passes through the planet's atmosphere, which is a daunting task. Nonetheless, Webb can closely examine a few of the closest potentially habitable worlds. Since it was not built to search for extraterrestrial life, and it is limited to tracking changes in the concentrations of methane, carbon dioxide, and water vapor, Webb cannot detect the presence of free oxygen, which is the strongest evidence that something is happening under the surface, even if some combinations of the gases may be reminiscent of life.